Lightning arresters, or surge arresters, are a device that is installed to protect homes, structures, and power lines from dangerous surges of power. As you might expect, the primary defense is against lightning and the damage it can cause. However, residential surge arresters also provide defense against surges from other sources as well. Lightning arresters are devices installed to shield power lines, homes, and structures from dangerous power surges. As the name suggests, they're primarily designed to safeguard against damage caused by lightning strikes. However, they can also protect the structure from various other sources. Lightning arresters are cylindrical objects, 1 to 2 feet long, consisting of a series inductor and a spark gap. The circuit which is protected from the strokes of lightning with the help of a protection device is known as lightning arrestor. Here the lightning strokes are nothing but surges with high transient voltage, arcs of isolation, spark, and surge currents because of lightning, etc. The fundamental working principle of a lightning arrestor involves the diversion of high voltage surges. When lightning strikes or a high voltage surge occurs, the arrestor provides a low resistance path to the ground. This path bypasses the electrical equipment, thereby protecting it from damage. Once the surge has passed, the arrestor returns to its normal high resistance state. A lightning arrestor, also known as a surge diverter or surge arrestor, is a protective device used to protect electrical equipment and appliances from the harmful effects of lightning strikes and overvoltage transients. It is usually installed at the junction of a power line and electrical wiring that enters a building or equipment. In technical terms, a lightning arrestor is a grouping of one or more gaps arranged in series so that the striking voltage needed for the group as a whole is higher than the maximum voltage that can exist across the system concerned under operating conditions. Lightning generates voltage surges in different ways and they directly hit on your house. It can strike wiring of the circuit within the walls of the house. Lightning can hit an object close to your home to cause a surge like the ground or a tree. So it plays an essential role to protect the electrical devices and traction installation from surges. The proper protection for this device is very necessary to check the normal power supply of rolling stock for smooth running. Lightning arresters are typically installed near a critical entry point or appliance, including generators and electrical panels. When a bolt of lightning strikes, the arrestor activates and deflects the lightning to the ground, where it disperses harmlessly. Bear in mind that these components don't actually stop lightning strikes, as that would be too dangerous. Instead, they limit the electrical charge and divert it, giving it a safe route to pass through the ground instead of essential electrical devices. Working of lightning arrestor. The internal construction and working of a lightning arrestor is simple yet highly effective. It consists of one or more stacks of metal oxide varistors connected in series between the line and ground. Each varistor block has a defined breakdown or striking voltage above which it conducts rapidly. Under normal operating conditions, the voltage across the protected equipment and arrestor is below the varistor's striking voltage. Hence, the arrestor offers very high resistance, and virtually no current flows through it. However, when a lightning-induced surge raises the line voltage momentarily above the arrestor's rating, the varistors start conducting and provide a low resistance path to earth. This allows the surge current to be diverted harmlessly to the ground, thus preventing excessive voltage spikes from damaging equipment on the protected side. Once the surge passes, the varistors again become non-conducting. These devices are used to defend the power systems by forwarding the high voltage surges in the direction of the ground. And these power systems and overhead lines can also be protected by using ground wire or the earthing from the direct strikes of lightning. The lightning arrestor diagram is shown below. The arrangement of these devices can be done on the towers, transmission poles and buildings to give a secure lane to the voltage and discharging current. Here these can be occurred during the strokes of lightning toward the ground to defend the system from the induced problems of lightning. The key characteristics of lightning arrestors. Here are the main features of a fully functional lightning arrestor. The spark over voltage must exceed the abnormal or normal power frequency occurring in the system. Additionally, it shouldn't draw any electricity in regular operating conditions. It must break down rapidly due to any abnormal voltage above its breakdown value, providing a safe path to the ground. When breakdowns take place, the arrestor should carry the discharged electricity without sustaining damage. Also, the voltage across the element shouldn't surpass the breakdown threshold. It must interrupt the current after the breakdown the moment the transient voltage falls below the breakdown threshold. Question is about ideal location of a lightning arrestor. The lightning arrestor should be placed near the equipment it protects. It's generally linked between ground and phase in an AC arrangement and ground and pole in a DC system. Furthermore, AC systems contain a separate arrestor in each phase. Surge diverters are installed in extra voltage AC arrangements to shield the generator, busbars, circuit breakers, lines, transformers, and other components. Likewise, HVDC structures include an arrestor to safeguard against filters, reactors, valve converter units, and similar elements. Moreover, there are various types of lightning arrestors that protect different power systems. The choice largely depends on several common factors. The list includes the line frequency, voltage, weather conditions, reliability, and cost. How does lightning damage electrical equipment? From the above concept, lightning has a very high voltage. When the lightning strikes the electrical equipment or component with very high voltage as mentioned above, the electrical equipment cannot withstand the strike voltage. The electrical equipment affected by lightning, when very high amount of voltage hits any equipment, it automatically passes this high surge voltage to the device and damages it. High currents at fast wave fronts occur, causing large electromagnetic fields which are then induced into your electrical and data communication cabling. Equalization then occurs which can damage the equipment. These surges are very short-lived, momentary bursts of energy that drive tremendous amounts of current into an electrical circuit for a few millionths or a few thousandths of a second. How does lightning damage electrical equipment? Additionally, semiconductors are extremely common in electronics, and a lightning-induced surge will almost always exceed the voltage rating of these devices. This causes them to fail or alter their electrical characteristics so that they no longer function effectively. Damage associated with over-voltage exposure increases with electronic technology advances because the components tend to become smaller. As the size is reduced, so is the microscopic spacing of insulators and circuits within the components, which makes them more susceptible to over-voltage damage. Strikes come in two types: direct and indirect. A direct strike can immediately cause a fire in the system, and an indirect strike can induce a large amount of voltage as discussed earlier. In other words, lightning arrestor diverts the abnormal high voltage to the ground without affecting the continuity of supply. It is connected between the line and earth, i.e., in parallel with the equipment to be protected at the substation. The following are the damages that are caused by the traveling wave on the substation equipment. The high peak or crest voltage of the surge may cause flashover in the internal winding, thereby spoil the winding insulation. The steep wave fronts of the surges may cause external flashover between the terminal of the transformer. The highest peak voltage of the surge may cause external flashover between the terminal of the electrical equipment, which may result in damage to the insulator. A surge arrestor typically consists of the following components: metal oxide varistor MOV element. The MOV is the main component of the surge arrestor. It is a ceramic disc made up of metal oxide grains with zinc oxide as the main component. The MOV is connected between the phase conductor and ground and has a highly nonlinear voltage current characteristic. When the voltage exceeds a certain threshold, the MOV element begins to conduct and shunts the excess energy to ground, protecting downstream equipment. Housing or enclosure: the MOV element is housed in a protective enclosure made of insulating material such as porcelain, polymer, or silicon. The housing protects the MOV element from environmental factors such as moisture, dust, and mechanical damage. End fittings: surge arrestors are connected to the power system through end fittings. The end fittings are made of high-strength materials such as galvanized steel or aluminum, and are designed to withstand the mechanical and electrical stresses of the power system. Ground lead: the ground lead is a conductor that connects the surge arrestor to the grounding system of the power system. It provides a low impedance path to ground for the transient energy, diverting it away from the protected equipment. There are several types of surge arrestor commonly used in power distribution networks. These include station-class surge arrestors. These are large surge arrestors designed for use in substations and other high-voltage applications. They are typically rated for high surge currents and are used to protect large transformers, circuit breakers, and other critical equipment. Intermediate-class surge arrestors: these are medium-sized surge arrestors used in medium-voltage applications such as distribution lines and pole-top transformers. They are designed to protect equipment against moderate surge currents. Distribution class surge arresters. These are small-sized surge arresters used in low-voltage applications such as residential and commercial buildings. They are designed to protect against low-level surge currents and are typically installed at the service entrance to a building. Metal oxide surge arresters. These are the most common type of surge arrestor and are widely used in power distribution networks. They use metal oxide varistors MOVs to provide surge protection and are available in various voltage ratings and surge current capacities. Silicon carbide surge arresters. These surge arresters use silicon carbide SiC varistors to provide surge protection. They are less commonly used than metal oxide surge arresters but offer some advantages, such as a higher energy absorption capability. The type of surge arrestor used will depend on the specific application and the requirements for surge protection in that application. It is important to select a surge arrestor with appropriate voltage and current ratings to ensure effective protection and reliable operation. Surge arresters are used in a variety of applications to protect power distribution networks and equipment from overvoltage transients. Some common applications of surge arresters include substations. Surge arresters are used in substations to protect transformers, circuit breakers, and other critical equipment from overvoltage transients caused by lightning strikes, switching surges, or other events. Distribution lines. Surge arresters are installed on distribution lines to protect pole-top transformers, switchgear, and other equipment from overvoltage transients caused by lightning strikes or switching operations. Industrial facilities. Surge arresters are used in industrial facilities to protect sensitive electronic equipment from overvoltage transients caused by lightning strikes or power surges. Residential and commercial buildings. Surge arresters are installed at the service entrance of residential and commercial buildings to protect electrical equipment, appliances, and electronics from overvoltage transients caused by lightning strikes or power surges. Telecommunications equipment. Surge arresters are used to protect telecommunications equipment, such as cell towers and data centers, from overvoltage transients caused by lightning strikes or power surges. Overall, surge arresters are used in any application where there is a risk of overvoltage transients that could damage or destroy electrical equipment. The specific application will determine the type and rating of the surge arrestor that is required to provide effective protection. Lightning arrestor working principle is, once the voltage surge travels throughout the conductor, then it reaches the location of the arrestor where it is installed. So it will break down the insulation of the lightning arrestor for a moment, so voltage surge can be discharged toward the ground. Once the voltage of the system falls under the fixed value, then the insulation will be restored among the ground and conductor. Further, the current flow toward the ground will be stopped. When a traveling wave reaches the arrestor, it sparks over at a certain prefixed voltage as shown in the figure below. The arrestor provides a conducting path to the waves of relatively low impedance between the line and the ground. The surge impedance of the line restricts the amplitude of current flowing to ground. The lightning arrestor provides a path of low impedance only when the traveling surge reaches the surge diverter, neither before it nor after it. The insulation of the equipment can be protected if the shape of the voltage and current at the diverter terminal is similar to the shape shown. An ideal lightning arrestor should have the following characteristics. It should not draw any current during normal operating condition, i.e. its sparks over voltage must be above the normal or abnormal power frequency that may occur in the system. Any transient abnormal voltage above the breakdown value must cause it to break down as quickly as possible so that it may provide a conducting path to ground. When the breakdown has taken place, it should be capable of carrying the resulting discharge current without getting damaged itself and without the voltage across it exceeding the breakdown value. The power frequency current following the breakdown must be interrupted as soon as the transient voltage has fallen below the breakdown value. There are many types of lightning arrestor which are used to protect the power system. The choices of the lightning arrestor depend on the factor like voltage and frequency of the line, cost, weather condition, and reliability. Characteristics of an ideal lightning arrestor. An ideal lightning arrestor should possess the following characteristics: no current draw in normal conditions. It should not draw any current during normal operating conditions, meaning its spark over voltage must exceed the normal or abnormal power frequencies that may occur in the system. Rapid response to abnormal voltages. It must rapidly break down in response to any transient abnormal voltage above its breakdown value, providing a conductive path to the ground. Location of lightning arrestor. The lightning arrestor is located close to the equipment that is to be protected. They are usually connected between phase and ground in an AC system and pole and ground in case of the DC system. In an AC system, separate arrestor is provided for each phase. In an extra high voltage AC system, the surge diverter is used to protect the generators, transformers, bus bars, lines, circuit breakers, etc. In HVDC system, the arrestor is used to protect the buses, valves, converter units, reactors, filter, etc. Rod gap arrestor. It is one of the simplest forms of the arrestor. In such type of arrestor, there is an air gap between the ends of two rods. The one end of the arrestor is connected to the line and the second end of the rod is connected to the ground. The gap setting of the arrestor should be such that it should break before the damage. When the high voltage occurs on the line, the gap sparks and the fault current passes to the earth. Hence the equipment is protected from damage. Sphere gap arrestor. In such type of devices, the air gap is provided between two different spheres. One of the spheres is connected to the line, and the other sphere is connected to the ground. The spacing between the two spheres is very small. A choking coil is inserted between the phase winding of the transformer and spheres is connected to the line. Horn gap arrestor. It consists of two horn shaded piece of metal separated by a small air gap and connected in shunt between each conductor and earth. The distance between the two electrodes is such that the normal voltage between the line and earth is insufficient to jump the gap. But the abnormal high voltage will break the gap and so find a path to earth. The horn gap arrestor consists of two horn-shaped pieces of metal separated by a small air gap and connected in parallel between each conductor and the ground. Multiple gap arrestor. The multiple gap arrestor consists of a series of small metal cylinder insulated from one another and separated by an air gap. The first and the last of the series is connected to ground. The number of gaps required depends on the line voltage. The multiple gap arrestor consists of a series of small metal cylinders, each insulated from one another and separated by air gaps. The first and last cylinders in the series are connected to the ground. The number of gaps required is determined by the line voltage. Series connection. The multiple gap arrestor consists of several metal cylinders placed in a series configuration. Each cylinder is insulated from the others and separated by an air gap. Connection to ground. The first cylinder in the series is connected to the power line, while the last cylinder is connected to the ground. Voltage handling. The number of air gaps in the arrestor is chosen based on the line voltage it needs to handle. Higher line voltages require more gaps to ensure effective protection. Impulse protective gap. The protective impulse gap is designed to have a low voltage impulse ratio, even less than 1, and to extinguish the arc. Their working principle is very simple as shown in the figure below. It consists of two sphere electrode S1 and S2 which are connected respectively to the line and the arrestor. Electrolyte arrestor. In such type of arrestor have a large discharge capacity. It operates on the fact that the thin film of aluminium hydroxide deposits on the aluminium plates immersed in the electrolyte. The plate acts as a high resistance to a low value but a low resistance to a voltage above a critical value. Voltage more than 400 volts causes a puncture and a free flow of current to earth. Expulsion type lightning arrestor. Expulsion type arrestor is an improvement over the rod gap in that it seals the flow of power frequency follows the current. This arrestor consists of a tube made up of fiber which is very effective, isolating spark gap and an interrupting spark gap inside the fiber tube. Valve type lightning arrestor. Such type of resistor is called nonlinear diverter. It essentially consists of a divided spark gap in series with a resistance element having the nonlinear characteristic. The divided spark gap consists of some identical elements coupled in series. Each of them consists two electrodes with the pre-ionization device. Between each element, a grating resistor of high ohmic value is connected in parallel. Thyrite lightning arrestor. Such type of arrestor is most commonly used for the protection against dangerous high voltage. It consists of thyrite, which is an inorganic compound of ceramic material. The resistance of such material decreases rapidly from high value to low value and for current from a low value to high value. It consists of a disc whose both the side is sprayed so as to give the electric contact between the consecutive disc. The disc is assembled inside the glazed porcelain container. Autovalve arrestor. Such type of arrestor consists some flat discs of a porous material stacked one above the other and separated by the thin mica rings. The disc material is not homogeneous and conducting material also have been added. Therefore the glow discharge occurs in the capillaries of the material and voltage drop to about 350 volts per unit. Oxide film arrestor. It consists of pellets of lead peroxide with a thin, porous coating of litharge arranged in a column and enclosed in a tube of diameter. Out of the two lead, the upper is connected to the line, while the lower is connected to the earth. The tube contains a series spark gap. Metal oxide lightning arrestor. Such types of diverter are also known as gapless surge diverters, or zinc oxide diverter. The base material used for manufacturing metal oxide resistor is zinc oxide. It is a semiconducting N-type material. The material is doped by adding some fine powder of insulating oxides. The powder is treated with some processes and then it is compressed into a disc-shaped. The disc is then enclosed in a porcelain housing filled with nitrogen gas or SF6. How does an arrestor divert the lightning? An arrestor consists mainly of a metal oxide varistor MOV. It is a semiconductor that is sensitive to voltage. At normal voltages, it is an insulator, but at higher voltages, it becomes sensitive and a conductor of electricity. As semiconductor acts very fast at a quick switching speed, it is a perfect application for an arrestor to divert the surge current quickly. MOV is an open switch to normal AC voltage and a closed switch to lightning AC voltages. As soon as lightning strikes, it becomes activated and immediately conducts this extra current and passes it to the ground as a low impedance path. Surge arrestors are connected between phase and ground terminals. If we cut open any lightning arrestor, we can see the line terminal, which is connected to the phase live terminal, and this bottom terminal is connected to the ground. Main component of LA lightning arrestors is a column of ZNO pieces, which plays important role in LA working. If we look at zinc oxide characteristics, which are non-linear, ZNO offers relatively high resistance at a low voltage level and very low resistance at high voltage level. Lightning arrestors have a limited lifetime as the internal varistors deteriorate with each operation. Regular inspection and maintenance are essential to ensure their protective performance. Some best practices include visual inspections, regular checks for physical damage or contamination, testing, periodic testing of electrical characteristics to ensure proper functionality, cleaning, removing dirt, dust, and other contaminants that could affect performance, replacement, timely replacement of damaged or worn-out components, annual insulation resistance tests to check for contaminations, cracks, or leakages, 5-yearly replacement or refilling of explosion vents in tank-type models. Every 10 years, varistor blocks must be replaced even if the insulation is intact. Outdoor arrestors need to be kept clean and dry. Their connections should be inspected annually. Advantages. The advantages of lightning arrestor are, property damage can be reduced from strokes of lighting. Outdoor equipment of the substation can be protected, avoid damage in lines, outlet surges can be avoided, electromagnetic interference, simple to use. Disadvantages. The disadvantages of lightning arrestor are, it occupies more space, the installation cost is high. Main differences between surge arrestor and lightning arrestor. Surge arrestor installed inside the panel board while lightning arrestor are installed outside. Surge arrestor protects the installation from inside while lightning arrestor protects the equipment from outside. Surge arrestor protects the system from lightning, switching, electrical faults and other transients voltage and surges, while lightning arrestor are mainly used for lightning strikes and associated surges. What is a lightning rod? A lightning rod, also known as lightning conductor, is a metal rod, copper or aluminum or other conducting materials installed on the top of the structure, transmission and distribution towers, buildings etc. to protect it from the direct lightning strikes. Lightning is the electrostatic discharge between clouds and earth. If they hit the power lines directly, the system voltage may rise to a dangerous level which may harm the electrical installation and equipment. For this reason, a lightning rod is used to protect the electrical installation, equipment and devices from direct hit of lightning strokes. How to choose the best surge arrestor? Choosing the best surge arrestor will depend on several factors, including the specific application, the level of protection required, and the electrical system characteristics. Here are some factors to consider when choosing a surge arrestor. Voltage rating. Surge arrestors are rated for maximum continuous operating voltage and maximum discharge voltage. It is important to choose a surge arrestor with the appropriate voltage rating for the application. Current rating. Surge arrestors are also rated for maximum discharge current. The surge arrestor should have a current rating that is sufficient to handle the maximum discharge current that could occur in the system. Energy absorption rating. Surge arrestors are rated for energy absorption capability, which is the amount of energy that the surge arrestor can absorb during a transient event. The surge arrestor should have an energy absorption rating that is appropriate for the expected transient energy.